Visible.
Yeah, it's visible. Okay, so first we'll discuss the answers of the quiz. You guys got the answers, and like, yeah, Ruben.
No, I was just raising my hand for the first answer.
Okay, yeah. So particles spin like a football. True or false?
False.
Okay, good.
False.
Okay, good. And which of the second question? Which of the following points is true about particle spin?
Spin tells how particles get their magnetic properties.
Yes, good. And
Statement
hmm?
of
Yeah.
how fast particles rotate.
Sorry, Alia, your voices was not very clear.
Yeah. I also just wanted to mention that spin also tells us how particles get their mass.
Hmm. Uh, Interesting. Interesting point. Yeah, I don't think they notice it's true for some particles. Like for example, electron. It's true for some particles, not all. Some particles it's is, but the magnetic properties is universal for all the particles. Cool.
Oh,
Yeah.
yes.
Yeah. I should have noticed this earlier. Thank you for reminding me. Okay. What are the directions of spin that electron can have?
Spin up
Spin
and down.
top and spin up and down.
Yeah, spin up and spin down. Spin top and bottom, they are not the used terms. Like I think maybe a few people did put spin top, right? Yeah,
I think so, but
yeah.
okay.
Okay, so for the next question, which of the following values are valid spin for electrons?
Somebody already wrote it in the chat.
Yeah, Kostov wrote plus half and minus half. Absolutely correct.
Next is false. Yeah, false.
Yeah.
Hmm. Uh,
Antimatter is attracted to
Well,
matter.
it's not like
yes.
really proven or something, but on a theoretical basis, we can predict that.
Yeah, people have not, like, obviously they haven't experimented with black holes and antimatter. You can't create both of them in like a lab or stuff. But because matter, because mass as a concept is the current for model of mass says that there is no negative mass. Yeah, Higgs field, because of Higgs field, there is no negative mass, and be it matter or antimatter, they have the same properties of mass. That's why it's theoretically black holes can attract antimatter. In fact, the whole concept of Hawking radiation is comes from there only. We'll talk about Hawking radiations later. So next question: weight depends on gravity. True or false?
True.
True.
Yes,
True.
exactly, true. And mass is given by, I think Costa
Higgs field.
already. Yeah,
Higgs field.
Higgs field.
yeah, very good. Okay, so most of you guys understood what the questions mean and how you guys answered. The only place we saw that you guys had like a doubt, that was the antimatter wala question. So now, do you understand why it's false?
Yes.
Okay, cool. So Devangi, can you share the slide?
Yeah. Any other doubt from the last session
Hmm.
before we begin?
I'll give us a quick recap. Last session we discussed Higgs field. Yeah, Vidush.
No, I mean you can complete. Then I'll ask my doubts after
Okay,
the
so
last.
in the last session we discussed mainly we discussed what is the Higgs field and how particles get their mass. We discussed spin and then Higgs field. So I'll recap the Higgs field. So Higgs field is basically it exists everywhere, and the and when a particle moves through the Higgs field, it faces a resistance. Before interacting with the Higgs field, every particle is massless and can travel at the speed of light. But when going through the Higgs field, which exists everywhere, it faces restrictions. So it gets slower, and as it gets slower, it becomes a massive particle. And Higgs boson is basically a byproduct of the Higgs field, where we, like, the way we discovered the boson is basically we collide particles in like a very energetic way, in like very high speed particles and heavy particles, so that it creates a sufficient amount of disturbance around the space, so that the disturbances of the Higgs field, the disturbances of the Higgs field, it can be observed. So that is the Higgs boson. Your mass to a particle is given by the Higgs field only. The Higgs boson, they travel in the Higgs field. That's basically like how like strings. It's basically the strings how they travel. The particles, like the particles which go through the Higgs field and they face resistance. Those resistance are governed by like they exchange bosons, and that's why they experience the resistance. But outside the Higgs field, uh, you can't normally observe the bosons. That's why in particle accelerators, we try to create a hole, a puncture in the Higgs field by very high speed, high energy particles, so that we can observe the Higgs boson before it decays. Cool? Okay, Vidush, you had a question?
Yeah. So last last session, uh, you explained that it's not necessary that all of our mass comes because of the Higgs field. There is
Hmm.
a lot of energy inside us that constitutes for the mass.
Hmm.
So like for like each particle having a mass is said to be having a mass because of the Higgs field. So what about energy then? Then energy, does energy interact with something that makes it have be a mass, or it's a property like it's an intrinsic property for it right now?
Okay, so initially it was like before Einstein, it was thought that energy and mass are very different concepts. Like they're both different properties. In in the physics that you study in your school, you like you have mass and your energy, you solve them differently. But after Einstein, it was like his famous equation E equals to mc square. It basically showed that mass, there's technically nothing called mass. Your the mass is an illusion which is caused by restrictions of energy. Like for example, if we have a box, consider that we have a mirrored box, like all the sides of the box is mirrored and there is a flashlight inside. Now the flashlight has a battery, right? And the battery contains like battery works on chemical exchanges where it creates electricity. Now, when you switch on the light and photons escape the flashlight, the whole um, flashlight, it loses mass, right? It loses energy. Sorry, it loses energy because the energy that was stored inside the cell now is going out of that flashlight. But how was the energy stored inside inside the flashlight? It was stored as a form of chemical energy, and that chemical energy had a bit of mass. Uh, now if you weigh up one identical flashlight which was not turned on, and a identical flashlight with the same mass, same battery, which is turned on, turns out the flashlight which is turned on will gradually lose mass, like very tiny bit of mass, but still loses mass. And that's because that energy the photons have, which is escaping the flashlight, was uh, inside that battery, and it was stored in form of mass. Now if you close that whole box, like sorry, that flashlight inside a mirrored all-sided mirrored box. Now you turn on the flashlight. So you guys know that in front of a mirror, light like reflects, right? Now when you measure the whole box, even though the flashlight is on, you'll see no change in mass because the energy which is leaving the flashlight, yes, the flashlight's mass is decreasing, but uh, the energy of the photons, it's trapped inside the box only. So the energy is not going anywhere, even though it's massless. I'm not saying that photons are individually they have mass. Those photons are massless and they're traveling like how massless particles will, but that energy is confined in a space in that box, and that confined energy we are also reading as mass.
Okay.
Uh, it's a very absurd and counterintuitive concept. I know.
Also,
Yeah.
uh, we also discussed the theory last time that particles are nothing but excitations. So, if we consider that, then how would we differentiate between energy and something like particles? Yeah.
Energy and particles. Well,
Yes.
yep. That's what the relativity tells us. The string theory tells us that there is nothing called particles. There are only disturbances in the energies of fields, and those fields then, like some fields, they interact with the Higgs field again. Those particles get intrinsic mass, which becomes your massive particles. Now those massive particles interact with each other, and they exchange like through different forces, and even those forces have like energy packets, and and those energies that they exchange between each other. For example, sorry for example, in protons, you have the three quark system. That quark system has gluons, which like move from one particle to the other. We discussed that, right? Now that gluon has an energy. That force, the movement, it has some energy, and because of that energy, it's like moving, right? But when you zoom out from that particle, you see that like that energy is restrained. It's contained in that whole system, and that's how a part of the mass of the proton comes. So according to string theory and like a lot of relativity string theory, there's nothing called mass. Like mass is an illusion of energy. It's a very new concept, so it's one way to look at it, but it's we know for sure that energy and mass, they are basically same. It's basically all energy. It's just how that energy is contained.
Okay.
Okay, any other questions? Yeah, Urjit.
Yeah, so I had one question related to beta decay. So
Hmm.
while we were studying neutrinos, we understood how beta decay happens. So my question was that whenever beta decay happens, so is there a formation of a new atom or an ion? Because the I think
Hmm.
in my opinion the number of electrons remain the same, but
Hmm.
just one proton is turned into a neutron.
Hmm.
So
Uh, yeah, you're right. A proton turns into a neutron, but how does a proton turn into a neutron? For in this case, yeah, it does become an ion, but because your electrons do move around randomly, and also it can easily gain an electron from the surroundings. What's that word? Wait, I forgot the term. Devangi, what's that electricity where like you rub surfaces and you get charged?
Static electricity.
Static. Sorry, I completely forgot that word. Static electricity is exactly that. You rub two surfaces together, and that exchanges electrons. So, for example, if I take a balloon and I rub it on my hair, the balloon and my hair, they exchange electrons. So now my hair has ions. The balloon has ions. That's why they get like they behave funny. But you also see that after a while, it like settles down again and things go back to normal. And that's because after a point, after the electric potential energy grows to after a point, it takes back of electrons from other places, and that's why uh, your electrons are actually never in scarcity. Your whole universe and like every place, you get a lot of electrons, neutrinos, they're very abundant. So and like your lightning happens because of the same static electricity. Your clouds become very negatively charged, but at one point the lightning does come from the clouds and enters the earth, and after that the electrons are again balanced. So yes, in a beta decay, the fusion, that the nucleus does change and it does become an ion. But after that, but that molecule, that nucleon can easily gain another electron. Yeah, Ruben and Alia. Okay, first Ruben.
No, I was just saying something about the lightning. as you said, the lightning that we see is actually positively charged, right? It
Yeah,
goes
sorry,
from the ground to the clouds. The
yeah,
negatively charged one comes down.
yeah. The negative, the electrons come down. The electricity direction is up.
Yeah, we
Hmm.
can't see the negatively charged one.
No, no, no. We see the negative charge. We see this flow of electrons. We can't see the flow of electricity. Like the strike that we see, that strike is the flow of electron from the clouds to the Earth.
Okay.
Hmm. Yeah, Alia.
So I just wanted to ask that given that we don't even know if there are any more particles beyond those that we have already explored, is there any way matter can be created fully or destroyed fully?
Yeah. In matter antimatter collisions where matter meets antimatter, that happens. Like you take an electron, you take a positron. If they collide, both like the particles they get destroyed, and two gamma ray photons come out. So you basically turn like all the mass, the mass that these two particles had, you just converted them into pure energy in form of light.
Okay, thank you.
Any other questions?
No.
Okay.
Should we start with today's session then?
Yes, I guess.
Okay, I'll share my
Hmm.
screen.
Yeah, it's visible. It's visible for everyone.
Yes.
Okay, cool.
Yeah.
Big Bang, time and space were all created. So there's no question what happened before. So we don't know where, like in this diagram, it says at the end, it's like at the starting, it says quantum fluctuations. That's a theory. We don't know if it's quantum fluctuation. We don't know what happened, but we know that something happened, and due to that, the whole universe was formed. Yeah, Alia, you had a question?
No, I actually not lowered my hands in the
Oh,
last.
okay. So brief introduction. After when the universe was born, it was basically a soup of quarks and like particles and all. There was no atoms, there was nothing. It was just an opaque soup of space. Then and like space inside the space there were particles whizzing around, there were gluons, there were quarks, everything. So and that time there was also inflation. Like it was growing very rapidly, more than the speed of light, in fact. Like the space was growing more than the speed of light, in fact. Yeah, Vidush?
Uh, before the before the Big Bang, currently we only know about the particles, everything which existed, which actually helped the Big Bang to occur. It
Mhm.
Currently we only know that for now we know that it just appeared out of nowhere, right? Because
Yeah.
there is no theory for that.
Yeah. So something happened. Like there are different theories. Like for example, people say that it might be an entropy dip. Some people say it might be just like quantum physics being quantum physics. So we don't know exactly what happened, but we know that something did happen because we all exist. Okay, so like there, where you see the afterglow light pattern on the diagram, it's basically that's the cosmic microwave background radiation, which was the first light the universe saw. Yeah, Urjit.
Yeah, I had a question. So, how do we date the universe? As in, how do we fully understand if it's really 13.77 billion years old?
We do that by we know that the universe is expanding. We first try to understand how much expansion is going on through redshift. Basically, you guys know redshift?
Yes.
Okay, so due to redshift means that the object is going away from you. So we measure how fast the objects are moving away at distant galaxy and all. We measure how much is the redshift, and then from that we can understand how the universe is expanding. And then we see how much time the light is taking from a point to like coming here. For example, if we say like if something is 20 light years away, that light that thing emitted, that star or planet or anything, it takes 20 years to reach us. We measure that, and then we measure how much expansion is going on, and
So
from that,
basically, if I look in that object in the
hmm,
sky, that's 20 light years away from us. I'm looking at it how it was 20 years ago.
exactly. So yeah, you're looking at when it was 20 years ago. Like even for our own star, sun, the light from the sun
8 minutes.
takes, yeah, it takes 8 minutes to reach us. So for example, if the sun disappears suddenly tomorrow in the morning, you won't know that the sun has disappeared until the 8 minutes are over, because light and gravity and everything which is massless, it travels at the speed of light. So before that, it's impossible to know. No information can be shared. Okay, so basically, what happened after the universe, the gradual inflation of the universe, slowly the matter, the quarks, the soup, it cooled down, and slowly the nucleons formed. Then the electrons formed, and we had the first element, that was hydrogen. So initially, the universe was mostly like almost 95% hydrogen, 4% helium, and 1% lithium. So that's how the universe was, and there was nothing else, like no other element. So after that, slowly those particles, those molecules cool down. They become gas, plasma, and like gas. And slowly, here you can see the first stars about 400 million years after the Big Bang. Slowly, those clouds cooled enough to become nebulas, and then from those nebulas, there were pockets of high density and all. They started attracting more matter, and they formed the first star. After this, we'll watch a video of how stars are born. Yeah, Urjit.
So, like you said, so that there were only three foundational elements that were
Yeah,
formed.
yeah.
So, is that or so like now we have a lot of elements. So, is that all because of the interaction with neutrinos?
No, that's all because of stars. We'll cover
Okay.
that today, like how different elements came into being. Okay, Devangi.
Hanging from Orion's belt in the blade of the hunter's sword is a jeweled cloud known as the Orion Nebula. Space here is littered with small globs of gas and dust. These are protostars, baby stars in the making, stellar cocoons, cosmic tadpoles. They form in galactic nurseries like Orion from clouds of gas and dust mingled with the ashes of earlier stars that have died and exploded. But like all newborns, the young star faces a perilous future. Buried inside this dusty cocoon, where astronomers can't see with regular telescopes, a secret star is being born. As the baby star tries to burn its way out of the cloudy egg that sheltered and birthed it, radiation from powerful stars nearby eats away the cocoon from the outside. Too much outside radiation can burn away not just the cocoon, but the disk around the new star, leaving the star naked and alone. If the disk survives, it could make planets, first by electrical forces as particles randomly collide and stick, then by gravity as clumps attract each other. As a planet forms, it will scour its orbit of dust, leaving a telltale gap like the grooves in a record. Recently, astronomers using the new ALMA radio telescope have made the most detailed picture yet of what might be planets being born. They found dark grooves scoring a disk around a star known as HL Tauri, some 450 light years from here. The disk is about 22 billion miles across, about 4 times the size of the realm of the planets in our own solar system. Are these gaps sheltering planets? Are we seeing the curtain rising on a new set of worlds like our own? H.L. Torre is only 1 million years old, a blink in the long lifetime of a star. For a newborn sun, every grain of dust is a promise. It's morning in the Milky Way. Everything is still possible.
Yeah. Any questions? Yes, Urjit and Madhav, right? Yeah. First, Urjit.
Actually, I forgot to unraise the hand.
Oh, okay. Madhav.
Yeah, I have a question that how did even something happen? Like if there was nothing, the whole thing was black and then suddenly Big Bang Theory happened.
Hmm.
How did that even happen?
Honestly, nobody knows right now. That's one of the questions which nobody knows. Like what happened, what caused the Big Bang. There are different theories. For example, like one says that maybe or is it, before our Big Bang, maybe there was another universe, and all the particles like somehow just randomly came into one small thing and just exploded. There's one theory that. There's another theories like there are numerous theories. A few theories says that maybe it was a black hole before it. Our universe came from a black hole. The wormhole theory that so like basically there's a white hole, like there was a black hole which sucked in matter and the white hole which released matter. Maybe some people say that maybe that's how the start of the universe was. So basically nobody knows. That's a
Oh,
question which nobody knows the answer as of yet. Yes,
mm,
Alia.
Uh, yes, so I wanted to ask that my question was that here it showed that the birth of planets and stars. So when were our galaxies, the sun, and all the different things in our universe formed?
The birth of galaxies, right? You were asking about the birth of galaxies, how they were born.
Yes.
Okay, so for galaxies, it's a bit more clouded. We're not sure. People are not sure, but basically the main theory goes that maybe like before, like the first generation of stars which were born, they were not born inside a galaxy. So after those died, because they were the first generation star, which were very like rich in hydrogen. We'll discuss why rich in hydrogen means like how does it happen, like how stars die and all. So basically that will go into deep details later in this session and in the next session also. So like those stars were very massive, and maybe they formed the first black holes, and those black holes, they sucked in more cloud matter into it. It formed disks around, and those black holes ate other black holes, because most of the stars were this big only. And that's how the theory goes, that that's how slowly the galaxies formed, because each galaxy has a supermassive black hole at its center. Even our galaxy has that.
Yes, thank you.
Hmm. Okay, so any other question? Okay, so I'll hand over the control to Devangi to take this session forward.
Okay. So now we'll start with nuclear fusion. So, does anyone want to? Uh, does everyone know what nuclear fusion is? Would anyone like to speak about what nuclear fusion is, or anything before we start? Okay, so I'll show a video first about nuclear fusion.
Nuclear fusion. In this video, we're going to understand how 2 or more nucleons merge or fuse together to create something more powerful and meaningful. So let's start by talking about the word nuclear fusion. Nuclear means the process which involves the nucleus, and fusion in English means two or more entities coming together or merging together to form one single entity. So, nuclear fusion can simply be defined as the fusion or combination of nuclei. Scientifically, nuclear fusion can be defined as a nuclear reaction in which lighter nuclei are combined together to form heavier product nuclei with the release of enormous amounts of energy. For example, lighter nuclei such as lithium and helium, when combined together, form a heavier nucleus. The mass of the heavier nucleus is less than the initial reacting nuclei. The word heavier here is phrased in terms of energy release, which is usually very enormous rather than mass. Therefore, the law of conservation of energy is satisfied. Consider the example of two hydrogen nuclei combining to form deuterium. Here, one hydrogen atom combines with another hydrogen atom, giving deuterium, one positron and one neutrino. This deuterium, in turn, combines with another hydrogen nucleus to form a helium isotope. If two such helium isotopes are fused together, the formation of heavier helium takes place. These three steps of a nuclear process, where four protons are fused together to form the heavier helium-4 nucleus and enormous amount of energy, is a nuclear fusion reaction. The chemical equation for this nuclear fusion is as follows. Four hydrogen nuclei, when fused together, give rise to the heavier helium. But how is this enormous amount of energy being liberated from such a seemingly simple nuclear?
Okay, so this nuclear fusion reaction, it can be broken down into 4 steps. So we can like look at it stepwise.
I'm sorry, I'm not able to hear you very well.
Hello, am I audible?
Yeah, it's much better now.
Okay, just give me a second. My laptop hanged. Is my screen visible?
Yeah.
Okay, so in the first step, we can say like these are two hydrogen atoms. So for the nuclear fusion, only the nucleus takes part. So two hydrogen nucleus, they will combine and they will form a deuterium atom, a positron, and a neutrino. So a deuterium atom is basically it is an isotope of hydrogen. So do you guys know what an isotope is?
Yes.
Anyone
Yes.
who
No.
doesn't know? Everyone? Okay, so uh, right. Uh, so two hydrogen atoms they will combine and they'll form the deuterium atom, a positron, and a neutrino. So this happens in the first step of nuclear fusion. Then in the second step, so now we got a positron from the first step, right? So that positron will combine with an electron and it will give out photons. And because matter and antimatter can't, like when they combine, they will release energy. So we will get photons, and these photons will eventually get absorbed and give out more energy, or they'll break down into smaller photons. Then in the third step, so now from the first step, we have a deuterium atom, which will combine with another hydrogen atom, and it will give us a helium isotope of which is the helium-3 and a photon. Now, this helium-3 will have two protons and one neutron, and in the final step, two isotopes of helium-3 will combine and they'll give us a helium-4 atom and they'll give us two hydrogen atoms. So these are the four main steps which are included in nuclear fusion. Any confusion up till here?
Could we please go through the steps once more? There is a little
Yeah, sure.
confusion.
Okay, so in the first step, what happens is, so inside a star, we have hydrogen, right, as Panther said. So the atoms of the hydrogen, the nucleus of the hydrogen atoms, they will combine and they will form a deuterium atom, a positron, which is also called an anti-electron, and a neutrino. Uh, is this okay, or any confusion here?
No.
Okay. Then in the next step, so from the first step, we got an anti-electron or a positron, and we know that electrons and anti-electrons can cancel each other, right? So an anti-electron, it will combine with the electron and it will give out photons. Is that okay?
Yes.
Yes.
Okay. Then in the next step, now we already got a deuterium atom from the first step, and since there's already hydrogen in the star, the deuterium atom will combine with another hydrogen nucleus, and it will give us a helium 3 atom and photons. And then in the last step, two helium 3 atoms, they will combine to give us helium 4 and two other hydrogen
Could you
atoms.
please repeat step 3? I did not understand step 3.
Okay. So you remember we got a deuterium atom from the first step, this one.
Yes.
So now this is present and there's already hydrogen present in the star. So these two will combine and give us a helium 3 atom. Does it make sense?
Helium 3 atom, this helium 3 atom is not the form of helium that we know. So it's
Yeah,
still not complete.
right. It's an isotope of helium.
What we know as helium is helium 4. Yeah. Modi? Anna Modi?
Why is the photon produced here?
What?
Why is
Can you
the photon formed over here?
Photon is, you can say, assume it as a release of energy out here. The photon, because when these particles combine, they produce a lot of energy. So these photons are like the energy which is released from the reaction.
It's basically like I explained a few slides back, right? Some like in reactions, energy is released. So basically, the mass of one deuterium atom plus the mass of one helium atom, when we combine that, the mass of one helium 3 atom is slightly less than the some mass of the both helium atoms. Sorry, the both hydrogen atoms.
Hydrogen
So
atoms, right?
yeah, so that extra mass which is lost, that extra mass is in the form of the energy of the photon.
This
Okay,
photon is eventually like absorbed in gases and everything, but just for the, like, it has to be released because law of conservation of energy.
Yes.
Then in the last step, now from the previous step, we got a helium 3 atom. So now two of these helium 3 atoms, they will combine to give us a helium 4, the helium which we actually know, right? And two hydrogen atoms. Is this clear? Any doubt on this step?
No.
Okay. So now looking at the final result, we can, okay, now so if we like
Could you
take the
show
first step and we do it twice, we get two anti-electrons, and these two anti-electrons will get cancelled with one each electron, right? And from here we get two of deuterium atoms. So these deuterium atoms, according to step 2, will combine with the hydrogen atom and give us helium 3. And this is how we get two helium 3 atoms. And now these two helium 3 atoms, they will combine and give us helium 4 and two hydrogen atoms. Is this okay? Any doubt here?
Could you repeat step 4 as I did not understand step 4?
Okay, so step 4 was, okay, from here, did you understand how we got helium 3?
Yes.
So in step 4, two of these helium-3 atoms, they will combine and they will give us helium-4, the helium which we actually know, whenever we talk about helium, we talk about helium-4. So these two helium-3 atoms will give us a helium-4 and two hydrogen atoms.
Okay, thank you.
Okay. So this is like this is the final result. And to sum up everything, we use 6 hydrogen atoms, as you can see, like 4 here and 2 here. So 6 hydrogen atoms plus 2 electrons, the 2 electrons which will cancel out the anti-electrons, and we get 1 helium 4 atom, 2 hydrogen atoms, neutrinos, and 6 photons. And here if we take these hydrogen atom to the other side, we can cancel it and it will become 4 hydrogen atoms plus 2 electrons will give us a helium atom plus 2 neutrinos and 6 photons. Any doubt in this reaction? Is it clear?
Yes.
Okay. And since a lot of energy is released, so the net amount of energy released is around 26 mega electron volts. So any question about the nuclear fusion?
Yeah, I just have one question. So when you say 26 MeV, so how do we visualize that? As in how much charge would it be?
It's not.
Charge.
It's energy.
It's
It's not charge.
Oh,
it's
sorry, sorry.
energy.
I mean energy. How much energy can we? As in how many? How can we visualize that?
You mean like how much mass would convert into 26 mega electron volt? Is that your question?
I mean how can we actually picture 26 MeV? As in how large is it?
How large is that energy? Uh, I'm not quite sure how large it would be.
It's okay. So 1 electron volt is about the
1.6 into 10
energy.
to the power of minus 19 joules.
Yes, ma'am. So 1 electron volt is about that, and mega means
10 to
it's
the power of
multiplied
6.
by, yeah, it's
6,
multiplied
yeah.
10 to the power 6. So it might not seem like a lot, but we are talking about things that is like only hydrogen atoms, and those are very small. So when these things add up, and like this one reaction that you are seeing, that's happening like trillions and trillions of times in 1 single second in a star. So this 26 MeV, it really piles up a lot. So that's why
Right.
stars.
This is like
Uh,
net energy of one reaction, and
One reaction.
like we can't even number the reaction that are taking place. So a lot of energy is like whatever energy we're getting from the sun is due to nuclear fusion. So you can like see it in that way, how much energy is actually released through these reactions.
Right. Thank you.
Anyone else? Okay, so moving forward, we have Panta. Will you take over?
Yeah, okay. So first we'll discuss the types of stars, because like the reactions that go on, like this hydrogen reaction, it's common for every star that you see out in this night sky. But what happens when like what happens after that really depends on how massive the star is and what the temperature of the star is. So it's a short video of classification of types of star. We'll watch that first.
When you look up at the sky, you'd be forgiven for thinking that all stars are the same. But that's far from the case. In fact, there are lots of different types of stars, from brown dwarfs to white supergiants, that can be categorized according to their mass and temperature. as in this Hertzsprung-Russell diagram. Red dwarfs are small stars with temperatures cooler than that of the Sun. They are the most common stars in our galaxy and are less than half of the mass of the Sun. They burn slowly and so live for a long time relative to other star types. They are positioned below the main sequence on the Hertzsprung-Russell diagram. Red giants are cooler than the Sun, so they have a red-orange tinge to the visible light they emit. Living up to their names, the largest red giants may be over 100 times the size of the Sun. Red giants are stars near the end of their life. They come above the main sequence on the Hertzsprung-Russell diagram. Stretching across the upper regions of the Hertzsprung-Russell diagram are the supergiants that cover a wide range of temperatures. These stars are truly enormous. Placed in the center of our solar system, the largest of these, such as the red supergiant Betelgeuse in Orion, would engulf all the planets out to the orbit of Saturn. Like Betelgeuse, Rigel in the Orion constellation is also a supergiant, but it is a blue-white supergiant. Supergiants are high-mass stars near the end of their life. When a supergiant dies, it explodes as a supernova, then shrinks to become a black hole. There is a group of very faint but hot stars in the bottom left of the Hertzsprung-Russell diagram. These are called white dwarfs and are so faint that none is visible to the naked eye. They are very small and dense, formed when a main sequence star reaches the end of its life. White dwarf stars gradually cool over time until they no longer emit light. The smallest, dimmest, and coolest stars are brown dwarfs. They are at the bottom end of the Hertzsprung-Russell diagram, at the lowest part of the main sequence. They are also known as failed stars and are very difficult to detect, as they do not have sufficient mass for nuclear fusion to occur. The main variables in star formation are mass and temperature. It is these which produce the wide variety of stars we see, and many we can't.
Okay, so any question? In the next, yeah, go on. Sorry, I couldn't hear. Devangi, can you change to the next slide?
I have a question that I missed the name of the first star type. Could you please repeat that?
Which one?
The first star type you mentioned.
The first star type, that's red dwarf.
Yes, thank you.
Yeah, so this is basically that sequence only. So their main sequence stars are basically the stars which are right now in their middle ages, which shine stably. For example, our sun is a main sequence star, and here mostly this is divided into it depends on two categories, that's temperature and the mass of the star. So here is a chart you can see. O type, their usual mass is around like 50 times the mass of the sun. Our sun is somewhere between G and F. So like G is basically like one solar mass star only. So our sun is a G type star. A few people say that it might be like a middle of F and G, but it's basically F or G star. Then these are all main sequence stars. Then at the end of their life, they the stars which are like spectra G, K, or M type stars. These like the three bottom ones, they become giant stars when they're dying. We'll discuss how they die, and like the higher variant of stars, which like more massive. Okay. Alia, you were asking that you did not understand main sequence stars. Okay, so you saw how stars like use hydrogen, right, in nuclear fusion. So if the output of that star is stable, if it's having a stable nuclear fusion, that's a main sequence star. A main sequence star is basically, it's a middle-aged, like if you consider stars life cycle as like as humans, then yes, Ayan, you're right. They die because loss of hydrogen. After this slide, we'll talk about how stars die. So Devangi, okay. So what happens when stars get low on fuel? Stars, like every other thing, they have finite fuel. The hydrogen is not infinite. So eventually, most of the hydrogen gets used up, and it gets turns to helium. So the nuclear fusion stops because, like it only like initially it can only fuse hydrogen. And stars, because they're very massive, and it's like gas and plasma, right? So it's very massive. So gravity pushes everything down, but nuclear fusion basically acts opposite to the gravity, so that the star is stable. It has a stable size. But when the star loses its fuel, the nuclear fusion stops, or not as much as it used to. For that, the gravity will slowly crush the star, and like it shrink the star, and like it basically shrink the core where most of all the nuclear fusion takes place. Now the pressure and temperature at the core increases because it's getting crushed. Your molecules are they don't want to be like crushed together, but they are now squeezed together and are made to be near each other. So the pressure increases, and pressure and temperature, they are directly proportional. So if pressure increases, the temperature also increases. So as pressure increases, temperature increases, and at one point, like it's shrinking, at one point the temperature and pressure becomes ideal to fuse helium. Now before this, all the star was only fusing hydrogen, but now after hydrogen is almost over, and it shrinks down, at one point the star gets hot enough and and small and like squeezed enough, the core becomes small enough that it can start fusing helium. And the fusion starts again, stronger this time, because helium fusion creates more energy. This time the fusion wins rather than gravity, and the outer layer expands. So basically the star shrank, but suddenly the star again grew in size. That's why the red giant stars and supergiants, they're so big, because they're almost used up a lot of fuel, and with the helium fuel, with then the other fuels, it grows bigger. Right? Any questions?
Can you explain the last point?
Fusion starts again stronger this time.
Yeah.
Okay, so now inside the core of the star, the core is now was getting crushed, right? So the core shrunk in size, and after that, and at one point, the pressure and temperature becomes so high that the star can start fusing helium atoms. Helium atoms then fuse into carbon. In the next slide, we'll discuss how they do it. Alia asked, how does the star start to fuse helium? Okay, so because of pressure and temperature, like for fusion, you need very high pressure and very high temperature. That's why the stars are so hot, because they need that temperature. That's why fusion is so difficult on Earth, because uh, for that we need a lot of pressure and temperature. Even stars face the same problems. So it's much easier to fuse with hydrogen. For fusing with higher, more heavier elements, you need more temperature and more pressure. So as the core of the star shrinks, it creates more pressure, because the particles, they were first like maybe this distance, but now they're been squeezed together and they're made to be at a very small distance from each other. And these particles don't like that. They try to push back, but the gravity is strong enough to push it, like it shrink it more. That's why it increases temperature also. And eventually at one point, the core of the star, it starts fusing those helium atoms as well. And helium atoms, when they start fusing, they create even more energy, because like they're bigger particles which are getting fused. So that's why like the thing that the gravity was doing pushing, and suddenly the nuclear fusion, which was getting lowered, it comes back with a huge force, because now the fusion is creating with more energy. That's why the outer layer of the star, it expands, because it it heats the plasma also, so it expands, and that's how the star grows in size. Yes, Ruben.
What about hypergiant stars?
I'll come to that. Hypergiants are actually a misleading terms. They're subset of supergiant stars only. So they're not official terms, hypergiants. So hypergiants are the nicknames of stars which fall into the supergiant category but are even more massive. What are neutron stars? We'll cover that in the next session. Right now, we are covering how stars die. Neutron stars, black holes, white dwarfs, they happened after the stars die. So now we are tackling the question, how stars die. Okay, any question? Because in the next slide, I'll show how the helium fusion takes place.
Oh, I think Arnav has a question in the chat box.
Can the fusion due to helium increase the size of the star so that it's even greater than its initial size before any shrinking? Yes, that's how the red giants and supergiants are formed. Because initially the star was not that big. Yes, it was bigger than the sun, like current sun and all, but it was not as big as the stars are right now. But when it shrinks down when the hydrogen gets over, but then helium fusion starts, and it grows back again. It grows back again, and in fact grows beyond that, because because the energy released by the nuclear fusion of the helium, it pushes it outwards. Yes, the outer layer of the star, they get cooler. That's why it becomes more reddish rather than yellow or white, because it's much bigger now, and the energy, the photons, they take a lot of more time to travel up to the higher layers. That's why it's more red. But at the core, the temperature rises and the star grows, it multiplies. Like, for example, when our sun when it becomes a red giant, it will actually grow 200 times bigger than it is right now. We'll look into that also. Okay, so now I'll go to the next slide, and hopefully helium fuel, how helium acts like a fuel. So here I won't go into much details. So basically, the helium fuses to become carbon through a process called triple alpha process. Alpha particle that basically helium nucleuses. Okay, so here basically two helium atoms, they fuse and they create a beryllium atom and releases, and that gamma ray is basically a photon only. The photons that you saw in the last time when Devangi explained, these are the same photons, but they are just named gamma rays because that's a gamma frequency photons. So then the beryllium and the helium again fuses to create another photon and carbon molecule. So this is how the three helium atoms, they fuse to form carbon. Now this is another fuel. Any questions?
I had one question.
Yes.
So, by what I really understood of the last slide,
Mm.
was that stars can never die, as in if they start. So, is that only because if they have enough pressure and temperature, then only they'll start increasing, or
Exactly.
is there a level, as in, is there a metric to this too?
There is a metric to this. It depends on the mass of the star. A lot of stars. Okay, so okay, Devangi, next slide, because a lot of your questions will be answered here. Okay, saving grace or delaying the death. So after exhausting the helium fuel, the same thing happens to the star, and it contracts and heats up again. Again, that helium fuel, it's not it's not infinite. It is also finite. In fact, it's less than the hydrogen fuel that it had initially. Eventually the helium atom also gets used up, and it's mostly carbon. The star shrinks again. The same thing happens, and basically the star shrinks. I mean, by that star, I mean the core. Mostly the core shrinks. The outer layer expands and the core shrinks. So again, it contracts and heats up. So now here's the line in the second point. Now if the star is massive enough, the carbon also starts fusing. This happens in the high mass stars. In most of your average stars, it stops at carbon. Like once carbon is reached, it's done. It can't fuse. Like even though it crushes, after a point, the molecules, the nucleuses inside the atoms, inside the core, they have enough energy, enough resistance that they can create a stable form. That's how white dwarfs are created. We'll discuss these later in more detail, how white dwarfs and neutron stars and what's the main difference. Basically, the molecules, they sustain the crush. They at one point they don't let the core crush even lower, and that's why the core doesn't get any smaller, and that time the fusion stops. No more fusion for the average size stars. But for massive stars, like which are your supergiants, which later become supergiants and all, the story doesn't end there. Again, the star, the core, it contracts enough, and again the temperature rises, the pressure rises, and it becomes an ideal condition to fuse carbons. I won't go into details of how these fusions happen. They are very complicated. So carbon then fuses into nitrogen, oxygen, and again the same things happens after quite a while. The carbon fuel exhausts, and it gets even small. The core gets even smaller. That time the temperature, pressure rises, and when the core is getting smaller, the outer layers are just growing even larger. Like the outer layers are increasing in size. The core is getting smaller. After a while, your oxygen will start fusing. It fuses into sulfur and then silicon, like all the elements in between, like from sulfur, from oxygen to sulfur, all the elements in between, they're all producing trace amounts. And finally, then silicon fuses. Like after a point, when even the silicon, even oxygen is used up, you only get a silicon core. After a point, when like if the star is uh, large enough, it shrinks, and at one point the silicon also starts fusing, and it fuses to form iron. And all these numbers that you see the next to the elements, like nitrogen 14, oxygen 16, these are all at the atomic mass. Sorry, that is basically the sum of the protons and neutrons in the nucleus. So nitrogen has 14 atomic mass, that is 7 protons and 7 neutrons. Oxygen has 16, which is 8 neutrons, 8 protons. Sulfur is 32, 16 protons, 16 neutrons. Silicon is 28, like similar. And finally, silicon fuses into iron. Now, iron has the most stable nucleus of any element, and thus it can't be fused further for heavier elements. You can't fuse iron. Yes, Vidush?
Is there a reason why
Yeah.
why iron?
Yeah, the next slide, I'll explain why iron can't be fused into heavier elements. So I'll get back to you after that slide. So basically, yeah, iron can't be fused to get heavier elements. Now the fusion stops completely. Like there is no fusion at all, because everything that could be fused is now used up. Fusion stops completely, and gravity wins, because the mass of the star is still huge, right? So the gravity wins, and the core of the star gets compressed into like a single point. It depends on how big the star is, to what extent it will be shrunk down. But basically, the core shrinks down exponentially, like it very fast in split second. And that creates a lot of energy, your friction, your other energies which get released. And again, when it shrinks, there's a lot of nuclear energies that's released, because you basically break down the molecules itself. And that in that split second, the core of the star, it releases so much energy that it explodes. Like the outer layer of the star, it explodes, and that is basically what a supernova is. Yeah, Urjit?
Yeah, I have two questions. So, considering a very small star with not a lot of mass, so do all stars die in the form of a supernova,
No.
or is it just the large and the heavy?
The large stars, the average size stars which only fuse till carbon, they just the outer layer, it just fades out. Like for example, for our sun is not massive enough to go beyond the carbon fuel. So it will just fade out as a planetary nebula, like the outer layers. It will just like leave the star, and it will just like it will become a nebula. Supernovas, on the other hand, they create in that split second. They release so much energy that maybe like 100 billion suns will produce in their entire lifetime. So that's why supernova explosions are the most spectacular space event to be observed. And these supernovas explosion are so bright that you can see it from like the other galaxies also.
Could
Like,
you
hmm? Yeah.
could you please explain the last point again? I did not understand how fusion stops and it becomes a supernova.
Okay, so fusion can only happen when there are elements which can fuse, right? But but iron cannot fuse. It's impossible for iron to fuse into heavier elements. That's why, and all the other things, all the other elements are used up, because all that was left would have been turned into iron at this point, at this stage. So there's the nuclear fusion stops completely because there is no fuel for nuclear fusion, and gravity wins because the mass of the star is enormous, and it's most and like gravity, like shrinks down, like crushes everything. And when we are talking about very high gravity, very high mass, and a lot of gravity, it it shrinks the core to like unimaginable amounts. Like, for example, okay, I'll discuss this more in the when we talk about white dwarf and neutron stars. But a white dwarf is about the size of our Earth, but the mass mm, is like almost half. The mass of that object will be half of what the mass of the sun was. Okay.
Okay, thank you.
Urjit, you have a hand raised. Urjit, do you have a question? Okay, I'll maybe continue. Okay, any more questions regarding this slide? Okay, I guess we'll move to the next slide. Okay, so this is the onion layers of a dying star. Now you can see, like, as your new elements form, these elements come closer to the core. They get deposited because these are the heavier elements. Heavier, like for example, when you put sand in water, the sand settles down, right? Because sand is heavier, it's more dense than water. Similarly, in a star, the heavier elements, they come closer to the core. They fall towards the core. That's why there are different layers formed. Iron is the heaviest, so the core is completely made of iron. Yeah, Ruben?
Nothing. Sorry.
Oh, okay. So the core is completely made of iron. After that, there's a layer of silicon. Yeah, Vidush?
Is it is that the reason the core of the earth is made up of iron?
No, no. Our Earth was not made by the process of a star. The reason why Earth is like mostly made of iron, because again, to a point, yes, because the heavier elements settle
Our core is made of
near.
knife, right? Nickel and
What?
ferrous.
What?
Our
Yeah,
core,
yeah.
knife.
Yeah, nickel, like iron, and and other heavy elements in trace amounts, mostly iron. And that's because iron is very prevalent in the universe. And the main reason is this, because like anything above iron, like the elements which are heavier than iron, they're created in other ways. They're not created in stars. They can't be created in stars. Yeah, okay. So coming back to the diagram, so basically, the iron becomes the core. It basically deposits near the core. Most of the core now becomes iron. After above that, there's a silicon layer, then oxygen layer, and these all go by the weight. The mass. Hydrogen is the least massive, so it forms the outer layers. Yeah, Urjit.
Yeah, I had one question. So why do supernovas, as in, have a lot of colors? So like there are a lot of bright colors. So why are
The
they?
colors are there because of the elements. Like you can see, if you look at the color of a supernova remnants, you can actually predict what kind of how much of which element is there. there's a whole branch of chemistry, spectrogram and all, where it's basically if you pass light through an element, that element will absorb some portion of the light and not absorb the rest, and later that light will be released from that element, that molecule, because it needs to be stable. And that released light, that's specific for each element. So for example, hydrogen is red, like all the nuclear nebula pictures that you see where it's mostly red and all, those are hydrogen. All the blue green things that you do, it's mostly nitrogen and oxygen. Carbon is also maybe bluish, I don't remember exactly, but the colors that you see of a nebula, that represents what like how the chemistry of the nebula is. But we also use false coloring to color the supernova, right? Yeah, it also happens. It exaggerates the colors. Like those colors are still there, like most because it's mostly white light. What you receive is mostly white light because all the lights, they mix together and form white. But to understand what the clouds are really made of, scientists, they exaggerate the colors so that now if you know what to look at, how the colors represent, you can just look at a nebula and be like, okay, this has this percent, like the outer regions, this percent is hydrogen, this percent is oxygen, which you
Yeah,
can't do
just
from raw images. Yeah.
Panthu, I can just, if I can add over here, basically, Beta, what you said is very correct. And for these images, you generally see artist's redemption. Another thing is like all the colors, they cannot be seen by the human eye. See, we can only see a certain part of the electromagnetic spectrum, the visible part of the light. So the light that we are getting, the electromagnetic radiations that we are getting from these stars, they may not fall into the visible range, and hence we have the artist's redemption that if we were to see it, this is how they would look to us if it was possible. Hence, you see that all that color. And just one more thing, like what Panthu is touching upon, helium was first discovered in the sun. And later on, when we saw the absorption spectrum that Panthu is talking about, and later on, we discovered helium on the Earth. By this method only, by spectrography only, helium was discovered. So, just little thing to add.
How do we identify the colors of each layer? You mean the you mean the layer that is in this diagram, or like layer as in the nebula's layer?
I think
Alia?
she means this only, if I'm not wrong.
Yeah.
Maybe.
Please repeat. I did not hear it properly.
I think she means this diagram only.
Okay.
If
Okay.
I'm
No.
not
Oh, this diagram. It's just like they just colored it how they see fit. Like mostly, like this is not the actual colors of the like the objects, like all the elements. This is not the actual absorption spectrum. They just rendered it. Like again, this is also artist rendition. This is just for understanding. Like
Oh, so they just colored it just to make it like easier to identify.
yeah, they colored it so that that's easier to identify. Like if you actually slice up a core of a star, you won't be able to see the colors like this.
Yes,
So
I'm sorry, I was not able to unmute.
it's okay, no problem. Okay, so next slide, Devangi.
maybe we can give them the quiz now and continue in the next class. It's 7:20 already.
Oh yeah, I did not notice the time. Okay, cool. Um, we'll give you the quiz, and the next class we'll tackle why iron is so stable, and we'll start from what happens when a star actually dies, like after it dies, after the supernova or the planetary nebula. We'll also discuss how our sun will die.
I'm sharing the link. You guys can fill the form and then just let us know and you can leave the session.